In the previous lesson, you examined the way in which you can determine the rate law for a reaction by doing an initial rates experiment. And in the initial rates experiment, we were changing the concentration of certain reactants independently of everything else and monitoring the effect on the initial rate of the reaction. And the initial rate of the reaction is measured at time zero. So if you imagine a concentration versus time graph, something like this, the initial rate is what occurs right at the beginning of the experiment. So it's the instantaneous rate of change at that moment. Now, this isn't always the most practical way to study the rate law of a reaction. And so what we're going to do is look at a graphical method for determining whether a reaction is first, second, or zero order. And what we're going to be doing in order to do that is completing what is called the integrated rate law. Now the math gets a little bit complicated, but we're going to avoid the complicated part of the math and we're going to focus on the linear functions that are derived from the complicated math. So first of all, what we need to do is talk about what kind of an experiment this would apply to. The kinds of experiments that we will do are ones where we will monitor the concentration of a reactant or product over time. And as we monitor the change in concentration with respect to time, we'll collect data, and that data will be used and applied to various graphs in order to make a decision about whether it's first, second, or zero order. Now, the ways in which we will collect this data will depend on the type of reaction. So recall that at the very beginning of our discussion of kinetics, we talked about the various ways that we can monitor the change in concentration of a substance over time. So for example, we can monitor the change in the mass of the system, we could monitor the change in the pressure of the system. The experiment that we're going to do, we're actually going to do a titration every 10 minutes in order to determine the concentration of a reactant in our system. Now let's look at the derivation of the graphs that we need for our analysis. For a first order reaction, you know that the rate is equal to the constant times the concentration of A raised to the power of 1. That's first order. Now, if we look at this as a rate of change, we're monitoring in rate the change in concentration with respect to time. So that's what dA over dt means. Now, this has a negative sign because, as you know, if we're studying a reactant, its concentration is going to be decreasing over time, so it's going to have a negative rate. Now we're going to look at concentration in a more simplified symbol. We're just going to use C. So we can also say that rate is equal to dC over dt, and it's equal to Kc. Now this is where some complicated math happens, and we're not going to worry about the complicated math. If you want to review the complicated math with me, it's integration that we're doing, and integration is the opposite of taking the derivative. So unless you're in AP Math, you will have not learned how to take an integration. You're still in the midst of learning how to take derivatives. So with some discussion, I can show you how it works, but that's not really the focus. Okay, what we need to do is kind of think of, okay, some math happens, and after integration, this is the relationship we obtain. Okay. Now this is going to be a new symbol to people. This is ln. And ln is called the natural logarithm. So you know about logs because you have studied pH. Just going to do a little side note over here. With logs, when you put in your calculator log of 2. What you're asking your calculator to find is 10 to the what is equal to 2. So when we're looking at lns, okay, I can look at ln of 2. And what I'm doing here is I'm simply looking at a logarithm that's not base 10. When we write log, what we're not writing in here is that this is a base 10 log. So it's 10 to the what is equal to 2. Ln is what is called the natural logarithm. Okay? And when we type into our calculator ln 2, what we are saying is e to the what is equal to 2. Now e has a special value. And there are many things in nature that decay naturally according to this logarithm. The value for e is 2.718. So when you put into your calculator ln of 2, you're asking your calculator to tell you what e needs to be raised to, or what 2.718 needs to be raised to, in order to equal that value. So for your purposes, what you need to be able to do is find ln on your calculator. It's below the log button. Okay, and the inverse of log is e to the power of. So just like log has 10 to the power of as the inverse, ln has e to the power of x as the inverse. So this is going to be similar to switching between pH and concentration. That's our little side note about ln. Okay. What we want to do is look at this equation and then look at this rearranged version of the equation. So what I did was I moved the ln c over to the right-hand side. And what we want to do is connect this to the equation of the line y is equal to mx plus c. You can see the connection here. Y is our ln c. So let's look at what graph we're dealing with here. Ln of c. The slope of this line is negative k. The x value is t. And the intercept is ln c naught. So what this integration gives us is the equation of a line for the graph of ln c versus t. And ln c versus t, when you have a first order reaction, ln c versus t gives us a straight line. The intercept, the y-intercept, is ln of the initial concentration, and the slope of this line is negative k. This is what's important to us. It's what you'll see in a minute when I summarize and emphasize this again. We want to take the data that we collect from the lab, so we're going to collect data of concentration versus time, and we want to know if this is a first order, second order, or zero order function. So what we want to do is take this data from the experiment and put it into this graph. So I'm going to take ln of each of my concentrations, put it against time, and if I get a straight line for that graph, then I know that the reaction is first order. So it's kind of like building this graph is a test for us. It's a test to see if the reaction is first order. If it does happen to be first order, we're also going to have the rate constant. And the rate constant is going to be the negative of the slope. Let's look at a similar scenario for a second order reaction. So for second order, you know that rate is equal to the rate constant times the concentration raised to the 2. Similarly, that's going to be the change in concentration with respect to time, so we can put it as dA over dt. We're talking about a reactant, so that's why it's negative. And if we let the concentration be C, then we have dC over dt is equal to kc squared. Okay, so this should actually just be C. Now, again, if you want me to discuss the integration with you, I can. It's really not that necessary, but if you would like to, I can. When we integrate this, we are given this relationship. And when I rearrange this to put it in the form y is equal to mx plus b, I can see that for a second order reaction, there is another graph that will give me a straight line. This graph is different. The y value for this graph is 1 over c. The slope for this is k. The x value for this is t, and the intercept is 1 over C naught. So for a second order reaction, the graph that's going to give me a linear relationship is 1 over the concentration of C versus time. This time it's going to have a positive slope, and the slope is going to be K. So the next couple of slides will summarize this, and then we'll do an example. And once the example is done, hopefully this will become a little bit more clear as to how this is going to be used. Okay, so just to summarize, for a first order reaction, you're not going to have a linear relationship when you have concentration versus time. But if you take the ln of the concentration with respect to time, you'll get a straight line. This is the equation of that line, and the slope of that line is negative K. One important note for this is that nuclear decay is a first order process. So that's an important point because sometimes you're asked to study nuclear reactions and you're expected to know that they occur in the first order. To summarize a second order reaction, if you looked at just the concentration versus time, you're not going to get a straight line. If you look at ln of concentration versus time, you're not going to get a straight line. What you're going to get a straight line for is when you graph 1 over the concentration versus time. You get a linear relationship with the slope equaling K and the y-intercept being 1 over A naught. And this is really helpful because remember from our last lesson, what we were doing is trying to figure out the rate law. And when we solved for the rate law, we also determined what the rate constant K was. Now we don't need to really do much with a zero order reaction, but we can discuss it. So with the zero order reaction, we know that the rate has nothing to do with the concentration of A. Okay, so it's raised to the 0. So the rate is simply equal to K. And what that means is that over time, the rate of the reaction is not going to change. So when you look at a graph of concentration versus time, when the order of the reaction is 0, what you get is simply a straight line. And the slope of this line is negative K. Okay, the concentration of A is simply decreasing in a linear fashion. So let's look at an example because it's the best way to really put this together and see how you need to be able to manage this information. So in your notes, you have in the second example that I give you, okay, with the 2NO2 going to 2NO and O2, you're given the time and you're given the concentration of NO2. So what has happened here is an experiment was done, and every certain number of seconds, the concentration of the NO2 was measured. We can assume here that they measured the pressure, for example, and they converted that into a concentration. So the data that you're given is the time and the concentration. Now what we want to be able to do is determine whether the reaction is first order or second order in NO2. And we also want to be able to determine what the K value is. So let's just look ahead for a moment and look at the graphs that I've created from this data. If you look at the graph of concentration versus time, so this is the concentration of NO2 versus time, you'll see that over time the rate is changing gradually. So this is not a zero order function, we know that. What we want to know is if it's first or second order in NO2. So we need to test the data. If the concentration versus time was linear, then we would know that it's 0 order. Okay? If not, then we need to check the next one. If ln of concentration versus time is linear, then we know it's first order. And if 1 over concentration versus time is linear, then we know that it's second order. So we need to manage this data. So in Excel, what I did was I took the concentration data and I took the ln of each value. So the ln of 0.01 is negative 4.6, okay, and so on and so forth. I also, in Excel, did 1 over concentration because it's easiest for me to just test both of these, ln and 1 over concentration versus time, and then I can make my decision. So let's look at the graphs that were produced. For the ln of concentration versus time, I'm showing you 2 different graphs here. It's the exact same data. The difference between my analysis here is what I've assigned the data to be. So in this graph here, which was my first graph, I forced it to be linear. So I added a trend line saying that I wanted it to be linear and I wanted it to show me the equation of the line. I also asked Excel to display the R-squared value. The R-squared value is a statistical value that really is showing me how close my data are to my trend line overall. When R-squared is equal to 1, that means that you have selected a perfect fit to your data. Okay, so when you see this, if you look at the data, you can see that it's not linear, okay, but you can also see it even more obviously by graphing the line and noticing that obviously it does not go through all of the data points. And my R-squared value is 0.9827. Okay, so this is not linear. So this means that this is not a 0 order reaction. This graph up here that I'm showing you, all I did was took the same data, and what I did was I asked it to be an exponential curve. So I asked it to have an x squared. And you'll see that my R-squared value is closer to 1. And you can also see that this line actually fits the data better. Okay, so this is a better fit to the data. A secondary proof that ln of concentration versus time is not a linear function. Confirmation that this is not first order. Okay, the next graph, I'm looking at time and 1 over concentration. So my y values are 1 over concentration, and my time is in seconds. This graph doesn't start at 0, 0. I've just scaled my graph so it starts at 99, so it's a little easier to see the data. And you can see from this one that it has a perfect linear fit. My R-squared value is 1. Okay, my equation of my line is given here. So this means that this reaction is second order. The other thing that's great is now that I've done the graph, I know that it's second order. Okay, so I know the exponent in the rate law for NO2 is a 2, but I also know that the K value for this is the slope of this line. So it's 0.5445. Okay. The units for this, I know because it's second order, are liters, moles, and in this case, the time unit is seconds. So hopefully you're feeling like you can use a different kind of data to determine the rate law of the reaction. That's what you should be feeling right now. This is just a different method for determining the rate law of the reaction. You're taking concentration and time data and you're testing it against the different graphs and making decisions from that.